that model. So here's what we're going to do. This number right here is a z-score, just like that 0 is. That 0 is a z-score. We take Brandon's 0.101, that's p hat, minus the 12% of the population. That's the observed flu rate from year to year to year to year. And we have to divide that by the standard error to see how meaningful. So let's do it. Root p q over excuse me, let me put the numbers in. Root 1288 over 1,000. So assuming you're drawing samples of size 1,000 from the population, that's what it's going to end up looking like. Let's crunch the numbers. Chris, ask me that question.
I can't read that.
Oh, sorry.
It's
It's because I'm smudgy. Hang on. I smudged it. My apologies. Let me write it better. P, which is 12%.
Right.
Q, which is the other 88%.
Oh, I got you.
Over 1,000.
Good.
I should have erased it properly the first time. Thank you for asking. Good so far? Let's see what it comes up being. You can't see that. There you are. You can't see that either, can you? Oh, okay. Okay. I'm going to do the denominator first. So the square root of 0.12, 0.88 over 1,000. Okay, there's my standard error. Just over 1%. That's pretty small, isn't it? It's pretty small. It's pretty small. It's small for two reasons. Give me one reason it's pretty small. That would be a margin of error of about 2%. If you doubled that times 2 to make it a margin of error, why is it so small? Give me one reason.
Your sample size?
Because the sample size is 1,000. Fantastic. Because your sample size is 1,000, number one. What's the other reason it's so small? This is a much more interesting mathematical question as to why it's so small. What else does it depend on besides just the sample size? That's definitely the good one.
P and Q.
The values of P and Q, you probably have forgotten this completely, and it's okay if you have. But the smaller that P gets, the smaller the margin of error gets. The product of these two numbers gets smaller as they get further away from each other. It's that parabola from like 3 weeks ago. We're pretty far to the left side of that parabola right now. We're nowhere near the vertex of 0.5, 0.5. We're now at 0.12, 0.88. So that's kind of, it's one of those interesting little things that the smaller this gets, the smaller the margin gets. That also explains to you why you need more of a sample to see a significant difference. We'll come back to that. I'm getting ahead of myself there a little bit. So good, our margin is but that. Now, let's divide that into this and see where we land, yes? And see where we land. Okay!
Wait a minute, did you
So I'm
subtract those numbers?
No, that, all I did, Chris, all I did was this calculation right here, right now. I'm now going to put that into these up here. This is just, all this is.
I got you.
You see, that's just the denominator. Rather than do the whole thing at once, I'm doing it piece by piece.
Yeah.
That way, number one, we can talk about each piece, and number two, I don't screw up the calculation somewhere. Good so far? Are we so far? Let's do it. So now I got to do 0.101 minus 12% all over that. Ready? Negative 1.85. We'll call open A5. Yeah? We now have an idea of where we are here. 1.85 what? This is good. Thank you, Brandon, for saying that.
Standard deviation?
Yes. Remember what you're doing when you calculate a z-score. When you calculate a z-score, you are creating a location on the bell curve's horizontal that tells you how many standard deviations away from average it is. Now that should be about 2 standard deviations. If the difference between this and this is about 2%, and the standard error is about 1%, it should be about 2 standard deviations down. 2 percentage points divided by 1% equals 2. Does that make sense? Ish. It's 1.84 with precision. But it's... Ask me that question, Brian. Ask me. You're just processing. You're just processing. Good man, good man. I'm sorry. I misread looks sometimes, as you know. So what we're saying is, yes, there's only a 1.9% difference between the sample value and the population value. But that represents almost 2 standard deviations away from average. Is that significant? Well, it sounds significant to me, right? I mean, almost we use 2 standard deviations all the time, don't we? We're constantly using 2 standard deviations all the time to give us an idea of, you know, of how far away are we now away, and is it far enough away to go, meh? It's almost like a song. So now the question is, are we far enough away to go, meh, that something has happened? Well, I don't know just yet, because what do I have to calculate? I'm going for the red marker. What do we have to calculate? Do you remember? We used the red marker quite a bit last week. What was the red marker always drawing on the curves?
Significant.
That level of significance. Remember this? We would draw that line, then we would shade this. And what was that area always last week? Do you remember what was most of the time last week? 5%. If we can find that area and compare it to 5%, I think we have our answer. You now have, I need a template for the number, sorry. You now know what the test statistic is. The test statistic is Z equals negative 1.85, which means it's down 1.85 standard deviations. The question for me and you is now, is that significant? Now that you know it's 1.85 standard deviations, does it seem significant to you? Numerically, statistically significant. Okay, Elizabeth's saying no. All right. What if this value comes up at 20%? I didn't draw it very well. If it was 20%, it'd be further this way, right? Would you think something has changed? That's a small p-value? What do we call small p-values? For conversationally right now, a small p-value is one that is an outlier, which means it's less than 5% of the time. What we're trying to see is, how much does this disagree with this? If this disagrees with this a lot, we're going to have a very small p-value out there. If it doesn't disagree with it a lot, we're going to have a big p-value out there. So what we have to know right now is how much area is right there. Can anybody figure that out for me? Based on the fact the z-score is negative 1.84, can you figure out how much area it is out there? In case you say no, it's totally fine. Your TI has a built-in that does this for you automatically. Let me show you what I gave my 243 students last term. Okay? I gave you guys a program called Stenormal. If I had asked you this in week 10 last year, you'd be like, duh, got it. But it's just been a long time. This is what we call a forward problem. We're shading left. The right bound is negative 1.85. Watch this, friends. Watch this. There's your curve. Whoops. Poop. Poop, sorry. It's a forwards problem coming from the, yes, left. Right bound is negative 1.85. Why is it shading all? Oh, there it goes. I must have put the wrong thing last time. Can you read that area? I don't know if you can. Don't worry, guys, don't worry about the program. Don't worry about it. Don't worry about it. This is the only time we're going to use it all term. Right now. Literally. There are other tools that are better. Other tools that are better. I just was getting that to get the area for you. To answer that question is, what is that? I got a 0. 3.22%. Is that small or is that big? Small, small, small. What does a small p-value mean? It's less than 5%. Something changed. The p-value is less than 5%, which means something changed. Oh, by the way, you now have, I think, number 8, right, on the template? Yes, you have the p-value. 3.2%, 3.22%. You got the p-value. Brian's still not convinced. Good for you, sir. Hold tight. We'll get back to that. I love your concern. I love your concern. This tells us we found a significant difference between the null hypothesis value, which was 12%, and our sample data. Now we report on our findings. This is number 9, the conclusion. Does it appear that our flu vaccine is working, or does it not appear that our flu vaccine is working? What do you think? Based on just this, it appears that it's working. Why? Don't worry about that. You're still not happy about the 1.9%. I get that. We'll come back to that, I promise. Why are you saying it appears that it's working? Which of the two hypotheses imply, let me kill the projector for a second. Which of the two hypotheses implied that the vaccine was working? It's 12% right in here. Which of these two hypotheses can be restated as the flu vaccine is working? H0 or H1? H1. When you get a large p-value, more than 5%, that means that your data and your null hypothesis are not disagreeing with each other. They agree with each other, correct? Big p-values mean you were expecting 12% and you got 12%. What do small p-values imply? You were expecting 12% and you got less. So we got a small p-value, right? So which of these two is easier to believe as a result of our sample data? Which of these two is easier to believe as a result of our sample data? This one right here. That's why we say it appears that the vaccine is working. Because it doesn't appear that it's not working. It doesn't appear this is believable. It appears this is believable. Said a different way, a more graphical way, it appears to me, friends, that there's another curve down here centered on our test statistic that shows lowered flu rates on our vaccine. Yeah? Could we be wrong?
Yeah.
Of course. How? How could we be wrong with our result? We just said, hey, it looks like your flu vaccine's working.
Could not be.
It might not be working, which means we could have made a what? A type 1 false positive error. Can we have made a type 2 error with our conclusion? Impossible. Because we didn't get a negative test result, we got a positive test result. So either it's a true positive or a false positive. So we could have made a type 1 error by saying the flu vaccine works, but it actually doesn't. That's a problem. That's a potential problem. Now, give me concerns at this moment. That's your first hypothesis test. Congratulations, you just crunched through it. Give me some concerns, Brian. Give me a concern.
Well, what's the z-value for 95%? So
Good. What is the z-value? Thank you for asking this, sir. What is the z-value for a 95% confidence? Now, clearly, thank you for this question, Brian. Can we see it on the camera? We can. I'm going to zoom in a little bit more. Thank you for this. Very, very good.